बिस्मिल्लाहिर्रहमानिर्रहीम। अस्सलामु अलैकुम। मुल्तान पब्लिक स्कूल and college and Multan. I am Qasim Qureshi, class O-Level-8, subject computer, teacher's name M.Qasim Qureshi, chapter number 2, communication and internet. Now I repeat the parity checking. First, parity checking is one method used to check whether the data has been changed or corrupted following transmission from one device or medium to another device or medium. Figure 2.6. First bit is the parity bit and 11011100 is the transmission of data. Parity bit is to be placed here, it is to be 0 or 1. Count your bits 1 bits 1 2 3 and 4. This is the even number, so 0 1 1 is the odd number. So when this is the even parity, then this is even parity, then we put 0 in the first box. Okay, if you use the odd parity, then you will put 1 in the parity bit. This is the same technique which is used in figure 2.7. Therefore, the byte just before transmission, either between even parity, then this is the even parity, then count 1. Even parity is, it means that ones is a even number, so you will put it is here 0. If this is odd parity, 0 is the odd parity, those you will put 1 is here it is. Now do the activity. Example number 1. This is a sender byte. This is a receiver byte. In this case, the receiver byte has 3 bits, 3 1 bits, which means it now has odd parity. While the byte from the sender had even parity, 4 1 bits. Okay, this clearly means an error has occurred during the transmission of the data. The error is detected by the computer recalculating the parity of the byte sent. If even parity has been agreed between the sender and receiver, then a change of the parity in the received byte indicates that a transmission error has occurred. So now move on to the activity 2.3, part A. Even parity used. Okay, then you count ones 1 2 3 4 5 6. Okay, all the ones equal to 6 digits. 0 0 2 digits. Okay, even parity then will be used, though it is a wrong, because 6 ones and 2 zeros is also even parities, both are. Okay, this is an error message. Now you count down in the another 1 in ones B part. Again even parity is to be used, no even parity. Again C part, even parity 1 2 3 4 5, no. Again in this case, where an error occurs, you can work out which bit is incorrect. Odd parity, naturally any of the bit example 1 could have been changed leading up a transmission error. Therefore, even though an error has been flagged, it is impossible to know exactly which bit is an error. Your last answer in activity 2.3 should have been no, since there is not enough information to determine which bit has been changed. Okay, all the bits is to be 1 2 3 4 5 6 1 2. No odd parity, all wrongs. One of the way around this problem is used to parity blocks. In this method, a block of data is sent and the number of 1 bits are totally horizontally and vertically, in other words. So now move on to the example number 2, page number 19. In the example, 9 bytes of data have been transmitted. Agreement has been made by that even parity will be used. Another byte known as parity byte has also been sent. This byte consists of entirely of the parity bits produced by the vertical parity check. The parity byte also indicates the end of the block of data. The following table shows how the number arrived at the receiving end. So byte number 1 is an even parity. Count ones. 1, 2, 3, 4 and 5. No, this is a 5, so it is a odd. Zeros. 2 zeros, so it is even. Count the number of bits of zeros is even, so this will be the 1 to be placed at the parity bit. Now careful study shows the following. Byte 8, row 8, okay, has incorrect parity. Why? Count it. First zero count. 1, 2, 3, 4. Even 1, 2, 3. This is the odd. So even parity is 0, 0, 0, 0. It means that we'll put at it will be here is 1. Bit number 5, column 5, bit 5, column 5, also an incorrect parity. There are 5 1 bits in bit 5. In bit 5, like it is here, it is. Parity byte is this. Here it is 0. Count it to be 0, 0, 0, 0. 4 parity bits 1, 2, 3, 4, or also got to be one place to be here. Okay. This is the example number 2. I think you understand. If you face some problem, then we'll be discussing the discussion chapters. This is also explanation. First of all, the table shows an error has occurred following the data transmission. Secondly, at the intersection of row 8 and column 5, the position of the incorrect bit value this. This means that byte 8 should have the value of like this, which would be also correct column number 5, giving an even parity. Vertically parity now has 4 1 bit. This byte could therefore be corrected automatically as shown above. An error message could be relayed back to the sender asking them to retransmit the block of data. So this is the example. This byte could reach the destination as this. This will be this. All there are clearly incorrect, but they are retained even parity. So this would not have triggered an error message at the receiving end. Clearly, we end to look at another method to complement the parity when it comes to this. Now you move on to another checking method, automatic repeat request. Automatic repeat request is another method used to check whether the data has been correctly transmitted. It uses an acknowledgement, a message sent by the receiver indicating that the data has been received correctly, and time out. This is the time allowed to elapse before an acknowledgement is received. If an acknowledgement is not sent back to the sender before timeout occurs, the message is automatically resent. Okay, this is the automatic request to repeat the sum and also correct it. Now to move on to the next checksum. Checksum is another way to check if the data has been changed or corrupted following data transmission method. Data is sent in blocks and additional value. The checksum is also sent at the end of the block of data. To explain how this works, we will assume the checksum of the block of data is 1 byte in length. This gives the maximum value of 2 raised to the power 8 minus 1, that is 255. The value is 8 bits is ignored in this calculation. Example 3 explain how a checksum is generated. If the sum of all the bytes in the transmitted block of data is less than or equal to 255, then the checksum of this value, However, if the sum of all the bytes in data block is less than 255, then the checksum is found using the simple algorithm. Suppose the value of x is this 1185. Then tracing through the algorithm, we get x divided by 256 equal to 4.629. Round down the nearest to the whole number gives y is equal to 4. Multiplying the y is 256. This is equal to 1024. Now the difference gives 161. This gives the checksum. This is the method to find the checksum of a number. Understand? Suppose the value is 1185 divided by 256 roundabout. Then multiply again this number to 256. First we divide this it, then again you multiply it. Okay, then you find the difference of this number. This gives the checksum of this 161. When a block of data is about to be transmitted, the checksum for the bytes is first of all calculated. This value is then transmitted with the block of data. At the receiving end, the checksum is recalculated from the block of data received. This calculated value is then compared to the checksum transmitted if they are the same value. Then the data was transmitted without any error. If the values are different, then a request is sent for the data to be retransmitted. Now you move on to the last echo check. With the echo check, when data is sent to another device, the data is sent back again to the sender. The sender compares the two sets of data to check if any errors occurred during the transmission process. As you will see, no doubt worked out. This is not very reliable. If the two sets of data are different, it is not known whether the error occurred when sending the data in the first place. If the error occurred, then sending the data back for checking. However, if no errors occurred, then it is called another way to check that the data was transmitted correctly. I think you understand the 4 checks methods. If you feel some problem, then we will be discussed in the inshallah Thursday lecture in the discussion lectures. Okay, thanks. Allah Hafiz.